Welcome to EPG Pathshala. In this lecture, we will be revisiting few of the concepts that we have already learned from our 10+2 levels. So this lecture will be dedicating to those concepts which you have learned in your 10+2 calculus. For example, function. What are the different types of function that we are familiar with? The series, their convergence, sequence, their convergence, etc. So for the first few slides, we will be spending time on different types of function, for example, one-to-one function, injective, surjective or bijective, those classifications, and how to find whether a function or relation is a function or not using vertical line test, and to check whether a function is one-to-one or not using some horizontal line tests. So these are the basic or preliminaries that will be required to understand the concepts of measure and, as a special case, probability. A function is a relation between set of inputs and a set of permissible outputs. That means that whenever we have something as output, it has some inputs, and we want to find the relationship in terms of function. And this property of relation is such that each input is exactly related to one output. That means we can't have two different outputs for the same input. If something like that happens, then it is not a function. Two different inputs may result in same output, that is permissible. So for two different inputs we may get same output. We'll show some examples. Let us focus on the picture we have. Here we have two sets, X and Y. The elements in X are denoted by blue dots, where elements of Y are just simple dots. Now all the elements of X, they have some connection to Y, though there are two elements in Y which do not have any relation with X. So whenever we are trying to formalize a function, it must be kept into mind that I can have two different inputs resulting in a single output, but the reverse cannot happen. If something like that happens, then it is definitely not a function. Now look into the next picture, the top one. Here we have X and Y. In the X set, I have elements 0, 1, 3, 4, -4, etc. And in Y, I have the elements 9, 1, 0, 16, etc. Now look into the element 16 in Y. 16 corresponds to two values of X, 4 and -4. So this is a function because every element of Y has a relation with elements in X. Moreover, two of the X elements correspond to the same Y. Now if you look into the next figure, which is in the bottom left, it is not a function because the element 6 in Y doesn't have any correspondence to any element of X. So this is not a function. So how to judge or how to test whether it is a function or not? To perform this, we can do what is called vertical line test. We plot the function x fx, and at any point of time or any point x, we just draw a vertical line, and if the vertical line crosses the figure more than once, then it is not a function. So this is known as vertical line test. This will tell us whether it is a function or not. The set X is called domain of the function, and the set Y is called codomain. And the set of elements that get pointed to the Y, that means the actual values produced by the function, is called range. So here we have three things: domain, codomain and range. Range and codomain corresponds to Y, whereas domain corresponds to X. Let us consider a few examples. Suppose the function is the reciprocal function y equals to fx equals to 1 over x. Now if you are asked to find the domain and range, it's not very difficult to obtain. Now this function 1 over x is valid for every value of x. I am talking about real values except x equals to 0. If x equals to 0, then this function is not defined. So domain will be all real x except x equals to 0. Now if you consider the range will be just like the same, all real values, but fx cannot be 0 because x is all real except 0. So y, that means fx cannot be 0. Now if we consider another example where fx is 1 over square root of x minus 4. Now we know that to define a square root, the quantity must be non-negative because I am talking about real values. So whenever I am talking about real valued function, then that means I need my square root element to be non-negative. To achieve this, I need the condition that x must be greater than 4. If x is greater than 4, that means square root of x minus 4 will result in a real value. So domain will be all real x greater than 4. For the range, well, fx can take any value since we are talking about only the real one. So x is greater than 4. That means square root of x minus 4 will result in only positive values. Hence, the range will be positive 1. That is fx greater than 0. Now we will try to figure out what sort of relationship or what different types of function exist. The first one we call it as general function, where we have two sets a and b, and all the elements in a are denoted by the blue dots and all the elements in b are denoted by the yellow dots. The first one says is a general function. It points from each member of a to a member of b. This is called general function. We don't have any other restriction. Now the second sort of function we called injective, where every member of a has its own unique matching member in b. That means I cannot have two different members in b for the same a, and on the contrary I cannot have the reverse also. So if you see all the elements, the first element in the set of a corresponds to the second element in the set b, whereas the second element in set a corresponds to the first element in set b, third and fourth, so on. So it means that every member of a has its own unique matching member in b. This is called injective mapping and sometimes one-to-one mapping. We can have a different type of mapping too, that is called surjective. Now what is the definition of a surjective mapping? Surjective means that every b has at least one matching a. That means for each of this b, I will have at least one element which belongs to set A. I can have more than one elements. Just see the picture, the third one. The first element corresponds to the second element in set B. The second element of A corresponds to the first element of B. Third and fourth elements of A corresponds to third element of B. That means two elements in A, they are corresponding to the same element of B. This sort of mapping is called surjective mapping. And finally we will have another set of mapping, that is called bijective mapping, where we have both the properties injective as well as surjective. So these are the three broad categories of mapping: injective, surjective or bijective. Now we will try to focus more on one-to-one functions. A one-to-one function that is called injective function is f from set x to set y is a function such that each x belonging to the set capital X is related to a different y belonging to set capital Y. So if we want to define one-to-one function more formally, it should be like something like that, that f is a mapping from x to y we will call this as one-to-one correspondence or one-to-one mapping if either of the two conditions hold. First condition, that if fx1 is equals to fx2, then it must imply that x1 is equals to x2. Or if we say in the reverse way, that if x1 and x2 are not equal, that means x1 not equals to x2, that implies that fx1 can never be equal to fx2. That means fx1 not equals to fx2. Let us consider the example fx equals to 3x plus 7. This is an equation of straight line, a simple equation. And here we are mapping from real line to real line. That means given the input x, they are all real valued numbers, we will be getting the output fx, all are real valued numbers. Now fa equals to fb, that means 3a plus 7 is equals to 3b plus 7. If I cancel 7 from both the sides, we will be left out 3a equals to 3b. That implies a is equals to b. Now fa equals to fb implies a equals to b. So by the definition or formal definition, it is satisfying the first condition, hence it is one-to-one mapping. Now if we consider another example where fx is x square. Here also we have same sort of mapping from real line to real line. But probably this is not one-to-one function. If you look it closely, then f of minus 4 will result in 16, whereas f of 4 will result in 16 too. So that means f of minus 4 is equals to f of 4, but minus 4 not equals to 4. So it doesn't satisfy the conditions for which I can say that this is one-to-one function. So that means fx equals to x square is not a one-to-one function. Now how to find or how to judge a function whether it's one-to-one, that means injective or not. Here we can do a horizontal line test. It says that you plot y versus x and you draw a horizontal line from the y-axis. Now if it intersects the graph more than once, then definitely it is not a injective mapping or one-to-one function. So horizontal line will tell that whether a function is injective or one-to-one or not. From the picture, the left one, it is not one-to-one mapping because for x1 and x2, these 2 points are different points. I am getting same y. That means f of x1 is equals to f of x2, whereas x1 not equals to x2. So this cannot be an injective mapping. But if you consider the next picture to the right, it is injective function because if x1 and x2 they are not equal, their functional value, that means fx1 and fx2 will not be equal to. That means the horizontal test will give you an idea whether a function is one-to-one or not. These are all about preliminaries of function which you have learned beforehand also. Now we'll try to focus on another function which is sequence of real numbers. A sequence of real numbers is a function from the set of natural numbers capital N to the set R. This is the real line of real numbers. So we define f is a function from N to R. Now if an is equals to function of n for all n belonging to the set of integers, then the sequence is a1, a2, a3, so and so on, or we'll write in this way, second bracket an. So this denotes a sequence. Note that a sequence is different from a set. Set and sequence, they are not equal. The main difference between set and sequence is that a number may be repeated in a sequence, but it need not be written repeatedly in the set. So in set we do not write the repeated numbers, but in sequence we have to write the repetitions too. So this is the major difference between a sequence and a set. Instead of sequence of real numbers, we can have a sequence of elements from any non-empty set S, such as sequence of sets, sequence of functions, and so on. We can consider these also. So it's not that we will be considering only the sequence of real numbers. Sequence of sequence sets, sequence of functions can also be considered. Given a non-empty set S, a sequence in S is a function. Once again, it's a function mapping from n set of integers to the non-empty set S. So this is the sequence of sets. Once we define the sequence of real numbers or sets or functions, the next job is to see the behavior of the sequence when we vary the n. What will happen if n becomes larger and larger and larger? So we'll start with few examples. First, consider the sequence, constant sequence, n is equals to 1. So even if I increase n, all the elements of this sequence or all the terms will be the same. So we call it as constant sequence. Now if we take an as n, so if n becomes larger and larger, an will become larger too, because an is just n. If I take the reciprocal function 1 over n as my an, then as n increases, it can be easily seen that 1 over n decreases and it comes closer to 0. If I consider another sequence where an is n over n plus 1, now as n increases, n plus 1 also increase. So the ratio, they are increasing almost in the similar pattern. So that means the ratio comes closer to 1. And last one, we take an as minus 1 to the power n. Now this term, all the terms of the sequence oscillates. When n is even, it's plus 1. When it is odd, it's minus 1. So terms of the sequence oscillates with values 1, minus 1 and plus 1. Now as n becomes larger and larger, n comes closer to a number, say a, if the sequence is convergent. So now we'll define what do we mean by convergence of a sequence. So by convergence we mean that whenever n tends to infinity, that means n becomes larger and larger, whether the sequence comes closer to a particular number, then that number will be regarded as the limit of the sequence. So this is the informal definition. Now if we are giving the formal definition of convergence. A sequence an in R, so we are talking about real number sequence made from the real numbers, is said to converge to a real number a if for every epsilon greater than 0 there exists positive integer n, in general depending on epsilon, such that whenever n small n is greater than equals to capital N, the positive integer, mod of an minus a is less than epsilon. That means the absolute difference between an and a is less than epsilon whenever n crosses a positive number capital N, and this a is called limit of the sequence an, and an is called a convergent sequence. Now the choice of capital N depends on the choice of epsilon. Different epsilon can result in different capital N. That is, the number capital N may vary as epsilon varies. We will show few examples. So if n converges to a, we write limit n tends to infinity an is equals to a. That means the limit of the sequence is a. That means the sequence is convergent and it converges to a point A. Now we can define this convergence into other ways also. Alternatively speaking, we say that whenever n is greater than capital N, then mod of an minus a is less than epsilon. That means an lies between a minus epsilon and a plus epsilon. So we define in this way that limit n tends to infinity an is equals to a if and only if For every epsilon greater than 0, there exists capital N belonging to the set of integers such that An belongs to the open interval a minus epsilon to a plus epsilon. Now An belongs to the open interval a minus epsilon to a plus epsilon for all n after some finite stage, and these finite stage may vary according as epsilon varies. That's why we are saying that this n depends on the value of epsilon, which is predetermined. Once we define the convergence in this way, now we have very important theorem that limit of a convergent sequence is unique. That means we cannot have two different limits for same sequence. To prove this, we will be using the method of contradiction. That means we suppose that the sequence has two different limits. So we will assume An converges to A and An also converges to B with the restriction that A is not equals to B. Now for every epsilon greater than 0, suppose we are defining two different numbers n1 and n2 belonging to the set of integers. n1 is for whenever I am considering An converging to A, and n2 is for whenever I am assuming that An converging to B. So by the definition we already given that An belongs to the open interval a minus epsilon to a plus epsilon for n greater than equals to capital N1, as we are assuming that An is converging to A. Similarly, we are also assuming that An is converging to B also. That means An belonging to B minus epsilon to B minus epsilon. So I have two open intervals a minus epsilon to a plus epsilon, B minus epsilon and to B plus epsilon, and An belongs to both of this. And this will happen whenever n is greater than equals to n1, simultaneously n is greater than into n2. So combining this, we are saying n is greater than equals to minimum of n1 and n2. Now we take the choice of epsilon to be mod of a minus b by 2. If I take epsilon is less than mod of a minus b by 2, then these two open intervals, they become disjoint. That means An belongs to interval 1, once again An belongs to interval 2, where the intervals are disjoint. This cannot happen. So this is a contradiction. So whatever we assumed that A not equals to B is not correct. So we must have A equals to B. This shows that limit of a convergent sequence is unique. Now we'll consider a few examples. First, the example we will be considering where An is 1 over n. The common sense says that if n increases, this will goes to 0. So limit An is equals to 0. Now we have to identify capital N such that 1 over n is less than epsilon for all n greater than equals to capital N. So it is easy to note that 1 over n less than epsilon implies and implied by n is greater than equals to 1 over epsilon. So if I take capital N as 1 over epsilon plus 1, now n is integer. To make it integer, I am using box function. So box of 1 over epsilon, that means the greatest integer contained in 1 over epsilon plus 1. So this is the n for which the limit goes to 0. Now we consider another example where we have the same sort of function 1 over n, but in the numerator we have minus 1 to the power n. If you take the modulus, it will become 1 over n, and we have already shown that this goes to 0. But we need to find the value of n, capital N. Here also we can write mod of n minus 0 is less than epsilon for all n greater than equals to box of 1 over epsilon plus n. So for both the functions 1 over n or minus 1 to the power n over n, we are getting the same n as box of 1 over epsilon plus 1. Now if we consider third example, 1 minus minus 1 to the power n over n. Here the limit will be 1. Why? Because if you see the second part of the function minus 1 to the power n over n, that goes to 0. So it is easy to note that this will goes to 1. So mod of an minus 1 is nothing but 1 over n, and we have already proved that for this the value of n will be 1 over epsilon box function plus 1. Now this is a tricky one. What will happen if it is a constant sequence? That means an is equals to c. If an is equals to c, then for every epsilon greater than 0, an minus c is always greater than 0, and I know epsilon is positive quantity. That means whenever n is greater than equals to 1, it holds. So for a constant sequence, it holds for n greater than equals to 1. Now we'll be considering more examples. Suppose an is 1 over n to the power 1 over k, where k belongs to the set of integers. Then also limit an is equals to 0. If I put this restriction 1 over nk is less than epsilon, that means n is greater than 1 over epsilon to the power k. So this will hold for all n greater than equals to box of 1 over epsilon to the power k plus 1. These examples shows us how to find the value of n, the finite number n, after which the sequence will converge. Now we'll focus on some important theorem when you have more than one sequences. So suppose I have only two sequences an and bn. An converges to a and bn converges to b. Now the question will be asking that what will happen to the sequence an plus bn or an minus bn. What will happen if I multiply a sequence with a constant of real number can, and I want to see how it converges. So the theorem says, suppose an is convergent sequence and bn is also convergent sequence. An converges to a, bn converges to b. Then an plus bn converges to a plus b, an minus bn converges to a minus b. For every real number c, can converges to ca. If an is less than equals to bn for all n belonging to the set of integers capital N, then a is less than equals to b. And the last result, that is very important, is called sandwich theorem. It says if Cn is in between an and bn, that means an less than equals to cn less than equals to bn for all n belonging to the set of integer capital N, and a is equals to b, that means an and bn, both the extreme sequences, they are converging to the same number a or b, then the sequence which is in between a and b will converge to a. That means Cn is converging to a. Now one application of sandwich theorem we can see by this example. Suppose you are asked to find the limit of a sequence where an is 1 plus 1 over n to the power 1 over n. Now I can write 1 plus 1 over n to the power 1 over n as greater than equals to 1, because we are adding some positive quantity to 1, and it is obviously less than 1 plus 1 over n. The left one, that is 1, is a constant sequence, so even if I take limit it will be 1, and the right one is 1 plus 1 over n. As I take limit n tends to infinity, 1 over n tends to 0, so the right one also converges to 1. So using the sandwich theorem I can say that an converges to 1. What will happen if the sequence is not convergent? A sequence which doesn't converge is called a divergent sequence. And if an is such that for every m greater than 0 there exists some n belonging to the set of natural numbers such that an is greater than capital M for all n greater than equals to capital N, then we say that an diverges to plus infinity. And if an is less than minus m for all n greater than equals to capital N, then we say an diverges to minus infinity. We can have another type of sequence called alternating sequence. Whenever the two successive terms, if you take the product, it will be negative. So a1, a2 will be negative. That means if a1 is positive, a2 will be negative. Or if a1 is negative, then a2 will be positive. So if the product of the two successive terms are negative, we say it is an alternating sequence. Alternating sequence may converge or may diverge. If you consider minus 1 to the power n over n, it will be a convergent sequence. But if you take minus 1 to the power n, it will be a divergent sequence. Now we will focus on the definition of bounded sequence. A sequence an is said to be bounded above if there exists a real number capital M such that an is less than or equals to capital M for all n belonging to the set of natural numbers. And the same sequence is said to be bounded below if there exists a real number M0 such that an is greater than M0. So a sequence where all elements are less than some number is called bounded above, and if all the members are greater than some number, then we call the sequence is bounded below. A sequence which is bounded above and bounded below is said to be a bounded sequence. Then we have one important theorem: every convergent sequence is bounded, but the converse may not be true. This result can be found in any standard textbook of real analysis and beyond the scope of this lecture. By the end of this lecture, we'll once again recapitulate all the concepts of function, different types of functions, sequence, and the definition of convergence. Once we define this, in my next slide or next tutorial, we'll be discussing the concepts of series and its convergence.